I'm really excited to be here. Today I'm going to talk about some of the work that we've been doing in building hardware prefetchers using machine learning techniques. All of this work is a collaboration between the University of Texas at Austin and Google. And here are all my collaborators that have contributed to this work. So just to provide some context, memory stalls account for 40 to 50% cycles in the Google fleet, and it's sort of one of the biggest performance bottlenecks for fleet-wide efficiency. So if you all remember, in 2015, there was a paper from Google about profiling a warehouse scale computer, and they looked at a variety of applications from the data center, and you could see that memory is the primary bottleneck for most of these applications. And that remains true even today. The applications that I work with every day at Google, they're primarily bottlenecked by memory. So data prefetching is sort of a widely used solution to hide long memory latencies. You sort of learn about it in Computer Architecture 101. And the basic idea is if instead of waiting for data to return from memory, let me go ahead and predict what data will I need and prefetch it before it is needed. The problem here is that prefetching has not been very successful for Google workloads. In fact, before I joined Google, I sort of thought that prefetching was a very mature field and there wasn't really all that much to do. But once I came to Google, I sort of realized that prefetching just doesn't work for at scale for these workloads. And one of the reasons for that is a lot of existing prefetchers predict sequential or strided memory accesses. And Google workloads tend to be more complex and irregular. So any prefetcher that sort of predicts sequences or stride just doesn't work for these workloads. So in 2021, we published a paper which used machine learning to explore the limits of irregular data prefetching. And by irregular data prefetching, here I mean prefetchers that can predict irregular sequence of memory accesses. So this would be pointer chases or indirect array accesses, anything that doesn't fall in the sequential strided bucket. One of the results of that paper was that we had a machine learning based prefetcher called Voyager. So just to sort of give you a sneak peek into the results, these are on the y-axis is coverage, which is the percentage of cache misses that the prefetcher is able to predict and hide. And here I'm showing the coverage for two state-of-the-art academic prefetchers, best offset, which predicts strided accesses, and ISB is a state-of-the-art irregular prefetcher that tries to predict irregular memory accesses. And you can see that both of these prefetchers don't really do that well for Google workloads. They get anywhere from 10 to 20% coverage. And so the ML-based prefetcher that we propose does dramatically better and gets about 30 to 50% coverage on these really difficult workloads. And so most of this talk will focus on what were the challenges in designing Voyager and how we went about it. Voyager is still not practical, and so we've been doing some research in how to make Voyager practically deployable. And so I'll spend the last 20 to 25% of the talk talking about how we can practically reap the benefits of Voyager. So let me start by talking about Voyager. One of the key contributions of the Voyager work was that we realized that off-the-shelf ML models are not a good fit for the data prefetching problem. So by off-the-shelf ML models here, I mean like if we just took a vision model or a language model and we just tried to apply it to data prefetching, that didn't really work as well. And so one of the key contributions here was to develop a custom model architecture that exploited some unique properties or unique features of the prefetching problem. And another contribution here was we realized, as everybody does, that ML models are too expensive to deploy as real-time prefetchers. So, I mean, a typical hardware prefetcher will need to make predictions at the nanosecond scale, but these ML models are obviously too expensive to work, to do training and inference at that scale. So in the Voyager work, we did not fully solve this problem, but made significant progress towards it. But as I said, towards the end of the talk, I'll talk about some work which comes very close to fully solving this problem. Okay, so here's the outline for the rest of the talk. Let me start by giving some background on irregular data prefetching. I'll talk about Voyager, experimental evaluation, paths to practicality, and then I'll conclude the talk. Okay, so what do I mean by irregular accesses? So irregular accesses are any accesses that are not strided or sequential. They're common in many programs that have linked lists, trees, graphs, pointer-based programs, indirect array accesses. So here's just a cartoon of a program going through memory, A to X, X to B, B to C, C back to D. So very irregular. There is this notion of temporal prefetching that has been around since the 90s, I would say, where the idea is that we can prefetch these kind of memory accesses by memorizing correlations. So the observation is that even though these memory accesses are very irregular, they tend to be correlated. So in this case, we could learn that A is always followed by X, X is always followed by B, and B is always followed by C, and so on and so forth. And that's what we call a temporal stream. So it's a stream of memory accesses that is correlated. And then when we see one of these trigger accesses, let's say A again, we can replay the memorized accesses. So if we see A, we can predict X, B, C, D, E, Y, and so on and so forth. If we look at this problem from a machine learning lens, so at first glance, you'd think this is exactly like a natural language task. So given a word, predict the next few words. So given A, let's predict X, B, C, D. And this looks exactly like a natural language task. But there are a couple of really important differences. So the first difference is that the output space of the prefetching problem is in the order of millions. So if you think about the output space, it's any memory access in the program. And so if you think about the English language, it has tens of thousands of words. So the output space of a language model is in the order of tens of thousands. But the output space of a prefetching neural model can be in the order of millions. It really depends on the memory footprint of your program. The second challenge or the difference here really is what is the label that you would train your model on? Because so if I look at the sequence of memory accesses, the exactly next memory access may not be correlated with A. It may be some access that's further down in the memory access stream that's correlated with A. And this really happens because the core might reorder memory accesses, there might be parallelism. So the sequence in which memory accesses are issued doesn't always sort of correlate very well to what accesses are correlated in the program. So our solution our machine learning solution addressed these two issues. To address the issue of the output space being large, we used a hierarchical model. And so we had a separate model to learn the page and the offset. And a nice solution here would have been to have separate models for page and offsets. But the interesting technical contribution here was to sort of integrate these two models in a way so that the page model had some context about the offset model and vice versa. And for the labeling problem, the model automatically picks the label that is most predictable using a multi-label training scheme. So I'll spend most of the talk sort of talking about the first aspect here. There's more detail about the second one in the paper. So let's see what I mean about what I mean with a hierarchical model. So let's say we have a 56-bit cache line address. We can break it into a 50-bit page address and a 6-bit offset. So if you look at a 56-bit cache line address, there are millions of possible addresses. But once we split it, then we have tens of thousands of pages and exactly 64 offsets. So this already looks like a tractable problem. And so with this, we are able to reduce the output space by 30 to 60x. A naive model architecture here would look something like this. We could have a page model which takes the sequence of page addresses and predicts the next page. And we could take an offset model and take the sequence of page offsets and predict the next offset. But this naive model doesn't really work because we cannot differentiate addresses with different pages and same offset or vice versa. So let's look at an example here. So let's say we have address X. We split it into page P1 and O0. And then we have address Y, which has the same offset O0, but a different page P2. Now with this naive model architecture, basically you would get different page predictions, but your offset prediction would be exactly the same. And that's unlikely to be correct because there's no guarantee that X and Y would result in the same offset in the output. So the key sort of aspect of the Voyager model architecture is to have these two separate models, but to integrate them. so that the page model has some context about what the offset model is doing, and the offset model has some context about what the page model is doing. So as you know, each of these models has something called an embedding layer, which is sort of the input representation of the sequence of page addresses and page offsets respectively. And so we had a page-aware offset embedding, which basically takes in information from both of these embeddings and sort of creates a link. And now both models, in addition to using their respective embeddings, they also use this page-aware offset embedding. There are more details in the paper, but this is sort of the high-level view of how we integrated the two models. Here's some sort of a quick overview of the details of page-aware offset embeddings. We basically use a mixture of experts and use attention between page and offset. So if your input page embedding was two-dimensional and your input offset dimension was looked something like this, whoops. Then we take a scale dot product attention and then get the corresponding attention weights for the page-aware offset embedding. Yeah, so this is kind of the high-level overview of how the page-aware offset embedding works. And like I said, for the label, we basically pick the label that is the most predictable using a multi-label training scheme. The multi-label training scheme, essentially given a memory access stream A, B, C, D, correlates the current access A with multiple future accesses. So we assume that either B, C, or D could be predicted. And then we tried different ways in which we could pick the next access. It could be the global one, which is exactly the next one, B. It could be the PC one, which could be the next address by the PC that issued A. And so we used binary cross entropy loss to determine the most learnable label among all these possible options. So now let's look at some data here. So for methodology, we did performance simulation using irregular benchmarks from SPEC and GAP benchmark suites. We also had traces from Google Search and Google Ads, which we were not able to run through a performance simulator because they did not have all the right information to be able to run through a performance simulator, but we were able to do trace-based simulation for these workloads. And as baselines, we used a state-of-the-art temporal prefetcher, which is called ISP. We used a state-of-the-art stride prefetcher, which is called best offset. And then we used a state-of-the-art ML prefetcher, which predicts strides or deltas, and that's called delta LSTM. So these are our three baselines. And so let's start looking at Voyager on SPEC and GAP benchmarks. So the x-axis are different benchmarks, y-axis is speed up over no prefetching. And so here you can see all the different solutions. They do well, different solutions do well on different benchmarks. But if you look at Voyager, on average, it improved speed up IPC from 22.7% to 37.8%. So it's a 15% improvement in speed up across a wide range of workloads. And just to provide some context, I guess these days we sort of have a lot of accelerator and these neural network work. And so 15% kind of looks small. But for a mature area like prefetching, where we are kind of at this point used to very incremental improvements in the order of 1 to 4% range, this was a very exciting result. It said that there was a lot more to do to improve prefetchers than what we were able to do today. And for context, like 15% could almost be one CPU generation. If we look at Google workloads, I already showed you this data before. Again, Voyager was able to double the coverage compared to prior art. So have we sort of dramatically improved prefetching? To some extent, yes, we've shown that there is a lot more to do in improving prefetchers, but Voyager by itself cannot really be used practically. So let me first say how Voyager is better than prior art in terms of model overhead, and then I'll talk about some of the challenges in deploying Voyager. So compared to Delta LSTM, Voyager is already way smaller. It's about 110 to 200x smaller. And it is also smaller than ISB, about 5 to 10x smaller than ISB. So the storage is something that we could manage. I think there's been good work in the prefetching community to deploy solutions that have large storage overheads and to come up with sort of creative ways to deploy prefetchers with large metadata overheads. But it's the computational overheads for neural models that are prohibitively expensive. So even if I had unlimited space, it's really hard to sort of do all the computation that you need. Like for example, Voyager will take 18 microsecond per prediction on a V100 GPU, which is just really not the scale that you want for a prefetcher. And more fundamentally, Voyager is trained individually for each workload because the set of addresses that you have is separate for each workload. So you can't really train Voyager on one workload and then use it for a different workload. It has to be retrained for every workload. And this training is expensive, requires iterative training. It takes in the order of seconds per epoch. So again, not really doable for a hardware prefetcher. And just for some context here, a typical hardware prefetcher will be about 64 to 128 kilobyte in size. Voyager is in megabytes. And if we look at the computational budget for training and inference, again, the order of magnitude here is just completely different. So now that we've shown that there is this opportunity, what can we do to actually reap this benefit? And let me see how I'm doing on time so I can pace myself here. Okay. So yeah, now let me discuss some paths to practicality. Broadly speaking, we are pursuing two different paths to practicality. One is to use profile-guided prefetch training, which is to basically say, hey, let's say if we have a workload that we really care about, say Google search or Google Ads. And in that case, it is worthwhile to train a neural model to learn the memory access behavior of that workload. And so we can maybe do the training offline and then use the model for online inference. Voyager as is doesn't work for that, but I'll talk about some work that is actually able to do that practically. And then the second approach, which is completely orthogonal, is basically we're looking at, hey, this model is able to do something interesting. Can we sort of try to derive some insights from this model to design simpler prefetchers? So let me talk about both of these aspects individually now. So the idea of profile-guided prefetch training is you train the model for each application offline during a profile-guided optimization phase and use learned weights for online prediction. And something like basically applications that have a huge footprint in the Google fleet would be great examples for this. Like it's worthwhile spending resources to do offline training for such applications. The challenge to make this work is that the model needs to generalize across different runs of the same program. So let's say if I took an application and ran it again, it may not necessarily have the same set of addresses because of memory allocator differences. You may have ASLR. If you're working on physical addresses, the virtual to physical mapping changes. So even if you train on one run of the program, the next time you run on the program, the address vocabulary might be completely different. And so from the perspective of the neural model, you've changed the vocabulary of the program and won't really be able to predict. And so that's one challenge in deploying Voyager as a profile-guided prefetcher. The second problem is that the model actually, even if because we're doing the training offline, we still need to do online prediction. So the model needs to be sufficiently small for online inference. And so while we were working on this problem, what we realized, one of the key impediments here was that the use of addresses as input and output to the model is inherently problematic because the model size will always scale with the memory footprint. Even though we did the page offset breakdown, we use that hierarchy, inherently the use of addresses sort of fundamentally limits the practicality of these models. And like I mentioned, addresses change with every program run. So the model needs to be retrained for every run. And again, that's sort of the root cause of this, is that we are using addresses, which is not at a sufficiently high level of abstraction to sort of represent program behavior. It's a very low level view of what the program is doing. So the idea here is, well, can we do temporal prefetching without using addresses? Which sounds kind of strange because temporal prefetching, the whole idea is to learn address correlations. But Kwong, who's one of our PhD students, has some really interesting idea in being able to do this. And so let me just sort of give a sneak peek of what he's trying to do. A key insight is that Voyager's output space is all possible addresses. So whenever Voyager is trying to predict an output address, it's trying to learn, it's assuming that the output can be any of these possible addresses. And so the state inside the model inherently needs to sort of learn this probability distribution from the input to all possible addresses. And that inherently is expensive because you're allowing the model to be able to learn a lot of different things. Empirically, though, each address is not followed by all possible addresses. Each address is only followed by a handful of successors. And so while the strength of Voyager is in being able to identify the right successor, it doesn't really need to consider the fact that the output space is all possible addresses for each address. So just for a concrete example, instead of learning that A is followed by X or Y, we can learn whether A is followed by its most frequent successor or the kth most frequent successor. And so with this way, so let's say we empirically we saw that each address is only really followed by 10 other addresses. And so now we've reduced the output space for each address from millions to about 10. And that is equivalent because that address is only ever followed by 10 other addresses. So we defined sort of a new abstraction for temporal prefetching. And so instead of using the neural model to predict the next address, we are now using a neural model to predict the distribution of occurrence of the top k frequent addresses. And this results in a model that is 30 times smaller and about 750 times faster. And it makes it, we think, sufficiently small so that it can be used for online inference. We're sort of still working on the hardware design to sort of make sure that it still can be, it has enough sort of practical area overhead. But I think we're really close. But more fundamentally, I think the interesting aspect of this abstraction is that it is able to generalize across different runs of the same program. So if I run the search binary again and again, if I run it tomorrow or a week from now, because we're not indexing on addresses, we're sort of using a slightly higher level of abstraction, the model is able to generalize. And we also found that it's actually even able to generalize very well across different inputs to the same program, provided we train it on a representative set of inputs, which is also a really exciting result because it's sort of, that's how profile-driven solutions, that's how we evaluate the quality of profile-driven solutions. So that was one path that we have been looking at to make neural models practical. I think this is super exciting. We're in the process of submitting a publication for it, and hopefully that'll be out soon. But let me also talk about this other direction, which I think is equally exciting, which is to basically look at neural models and see what they're learning and try to understand and derive insights to design simpler prefetchers. And so this line of inquiry sort of started with the question of why does Voyager actually work? And one of the answers to that question was that it's able to leverage a history of past addresses to predict the next address. So in particular, Voyager was able to use a history of 6 addresses to predict the next address. So like a typical temporal prefetcher would, when it sees E, it would predict F in this example. But what Voyager was able to do was able to look at longer context and say, hey, when it's A, B, C, D, E, I access F, but when it's X, B, C, D, E, I access G. And so Voyager is able to learn these correlations. So our thought was, can we build a simple table-based implementation to capture a long history of addresses? And so we did that. And so the green bar here is the Voyager neural model that we've been looking at throughout the talk. And here's sort of a naive table-based implementation of this. This naive table-based implementation is, again, currently not practical because that table is huge. And if you've worked in sort of branch prediction or any any sort of table-based hardware prediction solutions, you know that these tables grow exponentially with the size of history. So in this case, if I'm looking at a history of 6, basically my input combinations will grow exponentially. So right now this table basically grows exponentially, but we can also use techniques that, really cool techniques that we've developed in the branch prediction community to sort of have these tables grow linearly to make some of these tables practical. So that's another sort of line of work that we are pursuing these days. The interesting thing about the blue solution here is that it doesn't have a huge computational overhead. All the overhead is storage. But I think, like I said, I think we can leverage some insights from branch prediction to make the storage overhead tractable. So let me conclude the talk by saying that off-the-shelf models are not sufficient for building accurate neural models for hardware prediction problems. ML machine learning showed that huge opportunity exists for building better prefetchers. And I strongly believe that there's a big opportunity to build novel models under strict budgets here. And I took prefetching as an example, but I think if we are able to sort of find how we can practically deploy machine learning models, those techniques will broadly apply to any hardware prediction problem. And so there's an interesting space here in, first of all, building custom models to solve computer architecture problems, but then also to explore different deployment scenarios to practically deploy those models for hardware prediction. Yeah, and so we need new frameworks to apply machine learning in a practical manner. Our current hardware view of things is that predictors are trained online and do inference online. That may be a stretch for neural models, but I think if we get creative about how we train these models offline, to what extent are they trained offline, to what extent are they trained online, we can really practically deploy these models for hardware prediction. So yeah, that's all I have, and I am happy to take questions.
Great. Thank you very much. And I have some questions, but I'll first throw it open to the room.
Hi, Akanksha. That was a very great presentation, and Disha. So the most exciting thing about your work was that you went all the way to learn like what Voyager is learning, history of 6 addresses. So I would like to know how do you get to know that what a neural network model is learning? Is there some profiler? What is the tool?
Yeah, that's a great question. I think a lot of that ends up being trial and error, which is why I kind of put that path as a second one and not the first one. So we demonstrated we had one success story with this kind of thing with cache replacement. So we had a paper in Micro 2019 where we were able to completely distill a neural model down to a very practical hardware predictor. But yeah, how you go about it is very trial and error based. It's basically based on ablation studies. You change your inputs, you retrain the model, you try different things. And so then you sort of start getting a sense for, hey, if I dropped this piece of information, the model accuracy suffered really badly. So this piece of information seems important. So there's a bit of that. Another way that we went about it is when you have these attention layers, sometimes you can look at their weights and sort of get a sense for the attention layer is sort of assigning higher weight to this set of inputs and rather than to that set of inputs. So if I go back to the cache replacement paper, one of the interesting things we found by looking at the attention layer was that the model always had one weight that was very high. The position of that weight kept changing, but it was always only really one weight that was very high. And so that sort of gave us an interesting hook using which we were able to design other ablation studies. But we were not able to do something like that for neural models where multiple weights were high. So yeah, not a great answer to your question, but I think it's a lot of trial and error. There's some saliency distillation techniques that we tried, but they're not that informative sometimes. So yeah, I would say like, I think it's trial and error, but it's worth the exercise because like we showed in the cache replacement paper, if you are able to do it, then you basically have a hardware predictor that works. You know, you can train it online, you can use it for prediction online.
Thank you.
Hi, I assume you can hear me okay?
Yes.
Cool. So my major question is, what's the context you use to build a machine learning model? Like how many instructions you look back to predict the next, or how many addresses you look back to predict the next address?
Are you asking how many instructions does the model need to be trained on, or are you asking that for a given prediction, how many input addresses do we need?
Yes, for prediction.
So we tried a range here. I think eventually 6 to 8 was a sweet spot in terms of getting the most out of most prediction accuracy, but also the model not being super large. But I think beyond 16, we saw no benefit at all. But I would say 6 to 8 was a good size, and that's what we went with. So 6 input addresses to predict the next address.
It's
Now
only
that,
six to
sorry, go ahead.
sorry for interrupting you. If it's only 6 to 8 instructions or addresses, I assume its model is simple enough. Do you think it's still necessary to use neural network, or you can use a simpler machine learning model?
So 6 to 8 addresses. So remember, each address is 1 out of 1,000,000 addresses, right? So then you need to have these embeddings that basically convert addresses to some numeric values that the neural model can understand. It's the embeddings that are essentially huge because the space of addresses is really large. Once you have the embedding, then we've tried with a variety of different models, from LSTMs to CNNs to simple, just fully connected networks. We do get benefit from CNNs and LSTMs compared to just multi-layer neural networks. But I would also say, like, most of the complexity comes from designing the embeddings and not necessarily uh, the the core model per se. So it's the embeddings that are huge that take a lot of computational resources. And there's no way around the embeddings because we're working with addresses. As a contrast, like if you were doing branch prediction, then each input is just a bit, it's 0 or 1, but here it's an address. And so converting that address to an embedding is what's sort of expensive.
What's the feature size you use for each instruction, like the dimension in the embedding table?
Oh, sorry, can you repeat the question?
So like in the embedding table, for each address, you are going to assign a set of features. What's the number of features you associate with each address?
What's the number of, what's the embedding dimension?
Yes.
I don't remember off the top of my head, but I think it's on the order of 15 to 20, but it's been a while. But the embedding dimension is an important aspect because I remember I kept sort of trying to push for having a lower dimension, but beyond a point, we sort of needed a high dimensional embedding for this to work. But I don't remember the exact number off the top of my head. It should be in the paper.
Do you think it's worth trying a longer context? We try like input 100 or 200 instructions to predict the next one?
Definitely worth a try. I think at some point we ran out of computational resources to train the model. But yeah, I think the more we're able to scale this, it'll be interesting to see what we find.
Okay, thank you.
I also wondered, and you touched on it several times, including right before your concluding remarks, you could apply this to other domains. And the one that came to mind for me was value prediction. And you could potentially segment values in a way like you segmented addresses into pages and offsets. I wondered if you've given that any thought, or if you think that is potentially a good way to go.
That's a great idea. And there was a value prediction championship a while back. And one of the things we were trying to do there was not use machine learning, but use sort of some techniques from temporal prefetching to see if we can predict values. And there's definitely merit in that idea. And so to take that to the next step, I think using machine learning for value prediction is an excellent idea as well. I think value prediction will be more challenging than prefetching for two reasons. First of all, the latency constraints are even tighter than prefetching. And second is that value predictors, what I found, needed to be really, really accurate. So if you were not 99% accurate, you still saw performance loss. So in that sense, maybe neural models are a good idea because they tend to have higher accuracy, but I also felt like the bar was really high to design a good value predictor, both in terms of performance, accuracy, and latency requirements.
Interesting, thank you. And I also wondered, I think you again touched on it in a number of ways, but I wasn't quite sure I understood. In terms of coverage and precision, is Voyager sort of getting most of its gain from broader coverage or better precision, or?
I did not present precision numbers, but yeah, most of the benefit that Voyager is getting is with higher coverage, but the precision is really good as well. And I'm glad you brought up that point because, again, I think one of the important aspects of having a good a prefetcher that can be deployed at the data center is to have high precision. So most of our evaluation looked at performance of workloads in a single threaded scenario. But typically in the data center, obviously machines run at very high utilization. And so prefetch precision is super, super important. Voyager has fairly good precision. I think both will contribute to that, but the data that I showed, the benefits were largely coming from better coverage.
Interesting. And I wonder, since you're getting so much from precision, if there's potentially some potential energy benefit, because whenever you have to do something fast at the last minute, like pulling in data, you have to often sort of move things around faster, have more complicated mechanisms. If you're able to do this effectively, I wonder if you can do things at a more leisurely pace and hence a more energy efficient pace.
I think it'll depend on when the trigger for the prefetch comes in. And I guess one idea here could be to try to predict with an older trigger. So instead of using, let's say, A to predict the next address B, you use an address which is 5 or 10 addresses ago. So that gives you more time. Yeah, that could be interesting, and that you're right, could give us some energy benefits. But that also, I think, makes the prediction problem a little bit harder.
Yes, definitely.
Hello, Akanksha. Hi. So one question is that, or two questions I have. The first thing is that you showed that a table-based approach can approach the performance of Voyager, right, on neural network model. So, and in principle, you can use like an n-gram model, like they use language modeling. So looking at 2 or 3 words to predict the next word, looking at the n words to predict probabilistically the next word, right? So you can have some type of n-gram modeling for address prediction.
Right, and I think this is kind of like an n-gram model. Basically, you take an input of addresses. I think the sequence helps to some respect, and I'm not sure if an n-gram model is respectful of sequences or not. Is that what you were getting at?
Yeah, I think like you have like given these words, what's the next word? So like looking at the past and words to predict the next word.
Yeah, and that's exactly that's exactly what we're doing. Basically, we're thinking of prefetching as like an n-gram model, n-gram prediction problem.
The other question is that couldn't you use like a encoder decoder architecture like a transformer? So instead of a large language model, you can have a large address model and just train it with all the work addresses that you encounter in the workload, and it would predict, right?
So let me first say this was not a large language model. It is much smaller than a large language model.
But do you think it's benefit like a large transformer-based model for this?
That's something we definitely discussed, and I think it just comes down to realistically how much compute we want to throw on the problem. At the time, back, we didn't have, I guess, enough TPUs or GPUs for the research project to train. We tried a transformer, the one that we tried didn't really work out, so we needed to try bigger models, and we just didn't have compute for that. but there was all, so I definitely think that's interesting to try bigger models or even try a large language models and see what kind of data you would need to put in and what you get out of it. But I'm also wary of going to bigger and bigger models because comparatively the model that we propose is small by by machine learning standards, and even that is really difficult to deploy. So I think there's sort of two paths here. One is to see what else, how much more can we get with bigger models, and then the other path is let's assume we have a model that works really well. How can we get something out of it practically? We've sort of focused more of our efforts on the second one right now, largely because we didn't have compute to pursue the first. But I think that's a super exciting. I would definitely be interested in reading research on that.
Questions?
Great. Now, thank you very much, Akanksha. Very interesting talk, terrific results. Obviously, you've got a lot of questions in the room here, and we really appreciate it. So thank you for doing this.
Thanks for having me, and I'm glad I was able to do this remotely. So thanks for accommodating that as well.
Happy to do so.
All right. Thanks, everyone.
So thank you again. Bye-bye.